Okay, I ordered a grandfather clock. Well, it's skeleton clock, but it's pendulum driven. This pendulum, I just got this in. I ordered it on Amazon. It's got a pretty heavy weight in the box here. Probably, I'd say it's a good 5-pound weight. Yeah, it's probably 5 pounds, maybe something like this. Okay, this is, let's see. It's German, forgive me if I'm not pronouncing it right, Hermle. Okay, Hermle, I'm not sure I pronounce, I don't know German with a darn, but yep, made in Germany, I believe. Okay. This clock, there was a one for 158 bucks on Amazon, but this one was 149. I think it's a slightly older model, and you'll know the difference because the weight has got like this different bronzy kind of color to it. It kind of has that color. Okay, the color is a little bit different to the weight. You can hear how heavy that weight is. I think it's heavy. Okay, so I'm gonna take the time to, I just took out the box, there's the box down there. In typical Amazon fashion, they put a box in a box, you know, Amazon, you gotta love it. Yeah, box in a box. Okay, so I'm gonna go through this, and not too hard to hook up the pendulum. The top of the pendulum has a little hook. You just hook it on there inside, and the weight obviously gets hung on the chain, probably here. Okay, there's a little, right, probably hangs like that. So I'll go through it, look at the instructions, make sure I'm doing it right. And you can set the, fine tune the time here. If it's running slow, you turn it one way. If it's running fast, you turn it the other way. Okay, pretty cool clock for the money. It's an amazing price. And it's pretty heavy with the weight, so I got to find a place to mount it. Okay, here is the skeleton clock, and I just made a quick stand. Yeah, I know it's ugly. It's not meant to be something permanent. Just put together 2 pieces of square tubing. It was from an old project I had for something else. So we're just using it for the clock. It's just leaning up against the wall. Okay, this is more to observe. This is a pendulum clock and weight. I'm about to hang the pendulum, which is right here. Okay, I just put together this stand. Now we're going to hang the pendulum, put it on there, clickety click in the back, and then that little box right there, there's a weight in there, and we'll hang that. Okay, the clock is running on my cheaply made stand. It's just 2 square tubes with some threaded rod leaned up against the wall. That's all it is. Okay, and I'll put it in the house because I'm going to be observing the clock, watching the gear train do its thing. It also help keep time. We'll worry about putting this in some type of wooden case down the road, make it all pretty. Right now, skeleton clock on a skeleton frame, Texas style. Now, the clock did not like hanging at a diagonal, because if you look at the stand, it's diagonal coming off the wall, right? The feet in the bottom are further away from the wall than the top, obviously. The clock did not like that because it was sitting at an angle, and the pendulum didn't like it and wouldn't run very well. So I managed to put a couple pieces of, this is some thick material I had laying around. I just threw it on top of the rod, and even though it's not exactly perfect, the pendulum seems to be okay with it. We got a little bit of a gap there between the material and the pendulum, and yeah, the pendulum just hooks on there. See if I can show it to you. It's pretty easy. If you look right there, see if the camera will focus on it. It's having a hard time focusing on all this shiny stuff. Yeah, the camera's having a hard time here. Doesn't like shiny stuff. There it is. You can see it hooked on there. Right, the pendulum's just hooked on there. And that's the material in the background, just some some thick diameter steel pipe that I had. There you go. You see the top gear moving, that's the escapement gear moving up there. That's the 1 second hand basically moving. Or maybe, I think that's half-second strokes on this pendulum. I guess that's the way they are. Weights in front of the pendulum. So pretty cool. I'm going to be observing this. It dings every hour with a bell. But I'll be observing just the pendulum. I'll be taking some notes. I already wrote down the gear train ratios for all the gears. Getting a sense for a project that I'm going to work on. Yep, I know. Don't judge me about that stand. Skeleton clock, skeleton frame. Working great though. Just got this all set up today. Went to the garage. Fabricated a simple frame with some square tubing, some threaded rod. Looking good. The little dinger goes ding every hour.
Okay, let's talk about generating electricity using gravity. That's what this project's all about. It's not about, creating another gravity-driven, pendulum-driven clock, or even spring-driven, because there's those clocks too, which are great. So it's really important to understand the difference between using this type of clockwork with all this gear train and the mechanisms that are in there, the escapement wheel, all the gears, and everything that goes into developing and creating a clock that's specifically to be very accurate, right? These devices are created and the gears are created so that they keep very accurate time. So that's what these type of clocks do, and that's why they're designed the way they're designed. There's a big difference between that and using this type of setup to generate electricity. They're not the same thing. I'm not concerned about keeping exact time. That is definitely not a goal. If I want that, well, I'll buy a clock like the one you saw earlier in this video. They do a great job. They're awesome. I bought the clock because, one, I like pendulum-driven, weight-driven clocks, and two, I get to observe its behavior and come up with ideas. I can literally go measure different things off this clock. I can even measure the torque or the force that the pendulum's creating, at the force that's at the pendulum, and even at each of these axles if I really want to get down to it. Okay, so I'm going to talk briefly here about what are some of the differences. Well, these clocks and the way they're designed, they're usually designed to be 8-day clocks or a 30-day clock. In the old days, they used to have, I think they had 30-hour clocks, okay? So I'm not concerned about trying to run something for 8 days. That's just not practical. In a minute here, we'll dive into the math a little bit and just talk about, some of my observations and some of the things that I've researched so far and where I think I'm headed, okay? And why I'm making decisions that I'm making. But I would be happy with 24-hour mechanism. Okay, maybe even 12 hours to start out. And I'll talk about why it's most likely we're not going to be looking at a mechanism that goes for 8 days or 30 days. Because these clocks and the amount of weight or mass that's used to drive them, by the time you get to the final gear for the second hand, let's say, or the minute hand, the amount of force or torque that's being generated is extremely light. It's very, very small number. Okay, it's like not even, it's in inch pounds, not pound feet. Pound inch instead of pound feet. It's very, very small, right? And that's all calculated, and they know they're not concerned with, when you're building this clock, you're not concerned about generating a lot of torque. You're concerned about generating just enough torque to keep the mechanism moving. That's why you could just place your hand on the pendulum and the thing will stop. It's a very delicate balance, right? The device I'm thinking about creating, we do need some amount of torque, because later I'll talk about why we need that, what the intentions are. We're probably going to get into a little bit of hydroelectric, and I'll talk about why I'm going down the route of hydro, and how does this mechanism come into play if we're talking about hydroelectric, and why won't I just use the weight? If weight's driving this, why don't I just drive something off one of these shafts? Why can't we just do that? Well, I'll talk about some of the differences. Just real brief, hydro, it may not even be hydro meaning water, but it could be another liquid. It could be antifreeze, it could be oil. There's different viscosities and masses that may tinker around with, depending on what fluid we're talking about. Okay, so more like fluid dynamics, not necessarily hydro. But most people are familiar with the phrase hydroelectric, so that's why I said it. But we're to be more generic, fluid electric, I think, is probably a better phrase. Some type of fluid. It may not be water. And why would we use that? Why would we use a liquid? Because a liquid, you can be extremely granular. Okay? It's very easy to adjust the mass or the weight of liquid. Extremely easy. You can move it in the smallest of quantities. Okay? You can't do that really very well with weight. If you're trying to drive something directly off a shaft, and you're trying to drive some type of little generator, forget about it. What if it can only generate 200 milliwatts, 200 millivolts at a fraction of an amp? It's just not efficient. It's not practical. And it's very difficult to accumulate the wattage, if you will, at that level, because electricity at that level is extremely inefficient. Okay, that's why when we talk about voltage, 24 volt systems are more efficient than 12, 48 is more efficient than 24, so on and so forth. That's why high voltage systems are often looked at. If you think about even Tesla, they use high voltage. They don't use 12 volts because high voltage is more efficient. Okay, this type of mechanical system would generate probably milliwatts and millivolts. It just isn't practical to try to directly drive some type of generator off of this. So we have to be creative and think outside the box. And I'll get into some of my ideas about why I want to go fluid electric or / hydroelectric with this mechanism possibly driving, okay? There are some unknowns here. Going to be breaking some new ground. Not 100% sure all of it's doable, but that's part of the journey, right? So really cool. So I'm going to switch over to a spreadsheet, just talk briefly, we'll finish up the video, talk about some specifics. Okay, at the top here of the spreadsheet is just looking at water, kind of doing some math here on volume of water, the weight of water, just kind of getting an idea of what kind of mass or weight would I be dealing with. Okay. Keeping that in mind, because this is probably going to be the medium by which we're going to create electricity. I know a lot of people are going to have some questions, and we'll dive into that, not all in this video, but if you look at this figure right here, this is 0.196 of a gallon. What the heck are you going to do with less than a quarter of a gallon of water? Can't do much with that, right? Well, you can if you know what you're doing with it, okay? And we'll dive into some of the specifics later. For right now, we're going to talk about, just get into the feasibility. And by the way, we'll probably be creating a custom pump, my own pump, to pump this water. And no, it won't be electric, it'll be a mechanical pump that's going to move some of this water. These numbers obviously are not final. This is just some baseline stuff to get going. Okay, let's scroll down here. This is kind of the important part. Spent the last few days doing some investigation on There's two primary ways to drive these clocks, the mechanical clocks of the old days. One is you can use, as we saw in this earlier in the video, you can use a weight and a pendulum. Okay, weight driven. Okay, so you have an external weight. The other way is you can use what's called a spiral torsional spring. Okay, there's other springs too, but this one's called a mainspring. And I won't dive too much into it, but mainsprings have been around a long time, and they exist both in clocks and in watches. Okay, and they can get pretty sophisticated, but we just keep things pretty simple. Anyway, you can see here I'm doing some pretty heavy mathematics here to figure some things out. We're using some elasticity. We're using some material dimensions. We're talking about spring constant. We're calculating some torque. We're looking at different alloys, which the spring will be made of, so on and so forth, okay? All right. It's a balance. A lot of this is about proper balance, okay? So after spending about 3 or 4 days going through the math and really contemplating quite a bit of stuff, let me go over to, you'll see down here, this particular tab on this spreadsheet is called Torsion Spring Calculator. We're going to go over to the gear ratio and torque calculator. Okay. At the top here, this was the clock we just looked at. Its gear ratio is right here. You can see the gear ratio is like amazing, right? This is low, very low torque, right? These ratios are crazy. They're super low. Okay. So just kind of some reference points for what that clock is doing. Doesn't mean I'm necessarily going to copy that, but it's good to understand what some of the current designs are doing, okay? Okay, so I went through and looked at quite a bit of spring material. There's stainless steel, there's 1095, there's 5060, which is a type of steel. These are all known as spring steel. Without diving too deep into what spring steel is, basically they have, they resist wear. They're very good about retaining their springability, if you will. Excuse me, I get a little sip of coffee. So I went through this quite a bit. So there's a lot involved here. You have to be very careful about how you calculate what these springs can and can't do. So I looked at some different calculators and some different things going on here. I'm not going to dive into all the particulars because I've been through quite a few different iterations here. Basically what it came down to was, after I looked at this for a few days and really crunched some of the numbers, it's very borderline whether or not a spring could drive my design. Maybe it's doable, maybe. That's a little bit of an unknown, but it's kind of leaning towards no, at least not realistically. You can see down here this net torque is 1.32 pound-feet. That's not a lot. That's really low. Okay, that's not a lot of pound-feet. That would be the number of pound-feet and torque that this gear system, gear ratio or gear train would produce when it's all said and done. We're looking at this one right here, actually. All right, we start with 109. This is newton meters, but it gets converted to pound-feet for US. But the rest of the world uses newton meters, so I went with that and then just converted it at the end. 190 newton meters is what we start with, and then we do some calculations here and some math. We're using a 90% efficiency rate, which may or may not even be accurate, and we come up with 1.32 pound-feet. Boy, that is like cutting it very close. Probably not realistic, especially if this efficiency rate is not even 90% if it's lower. Okay, there are ways to change this input torque. There are ways to do that. We could come back over here to this other spreadsheet, the torsion spring calculator, and we can start monkeying around with the material width. Like right now I have a pretty stout material width, 6 inches. That's not thickness, that's just the width, left, if you can think of it left to right. The thickness is it's called 16 gauge. Pretty thick stuff. We're starting to get into some of you probably don't really know metal materials, and sheet metal and steel, they come in gauges, okay? And this is 16 gauges, 0.0598, or almost 0.006 of an inch thick. That may not seem like a lot, but that's a already become a pretty thick material. And trying to coil that up into a spring, into a main spring, the spring we're talking about, it literally would be like this. It just goes around, it keeps going around, it keeps going around, keeps going around. It gets bigger and bigger like this, okay? It sits inside of what's called a main spring barrel. Okay, and it slowly releases its power, and there's a ratchet on the side that controls the way it gets released. It releases iteratively along, and it works in conjunction with the clock mechanism and the gears and escape mechanism and all that, okay? So we're already kind of on the borderline whether or not we could actually take 16 gauge material and wind it tight enough to get inside a 5-inch barrel, because this is what it have to fit inside it. So obviously, there's some parameters here that can be adjusted. They're in orange. We can adjust the length. We can adjust the gauge. We can adjust the material width. We can kind of monkey around a little bit with some things. And I've done quite a bit of that, like I said, the last few days. And when it's all said and done, we'd probably have to go down to like 11 gauge material, maybe 12 or 14 gauge material, thicker material. It'd have to be pretty wide, half a foot. So we're getting kind of bulky. And there may be manufacturers that would be willing to pull it off, especially in China through Alibaba or something. They would probably do it, but in the end, I'd probably have to be making my own springs, and that means purchasing an induction furnace or an induction heater. I won't dive into what that is, but basically you heat up the material, and as it's being heated up, you coil it at the same time. It's almost like a hot forging. All right, that's probably where, that's probably where I would be heading to test my springs to see if they could work. Okay, so it's going down the bunny trail, right? You start going down the bunny trail and you realize, wow, I'm getting deep. This is a big investment. Is that doable? Yeah, but is it really worth it? Maybe, maybe not. Okay, so I think at this point, my point is I probably have exhausted exploring the spring approach. It's borderline, and I don't want to be working on something that's borderline. I want to be working on something that's confident. So guess what? The next thing we're going to check out I got to work up all the mathematics and the physics for weight and pendulum, which is different than spring. Yeah, I got to go through the mathematics and the physics for pendulum and weight, okay, which is totally different than you calculating spring torsion. All right, so that's, excuse me, that's why I haven't done that yet. That's what I'm going to be doing next. So that's where I'm at, right? There's going to be some other things that need to be designed ahead of time. I'm going to design a simple mechanical pump. It doesn't have to move a lot of water, guys. It's going to move a very small amount of water, really tiny volumes of water. And I'll get into why I'm thinking of it from that perspective. There's some other things I need to work out. Where exactly in the gear train am I going to be leveraging the torque? Is it at the pendulum? Is it at the final gear? There's some unknowns here. There's going to be some trial and error. I might buy another cheapy little pendulum and weight clock, not like the one I showed you in this video, maybe something kind of on the cheapy, and just experiment with it, and let's see how the gear train's affected when we start applying force against it. That's why I said I'm going to finish up with this. We're not trying to build a clock mechanism. Because if we do that, I guarantee the pendulum will stop moving. Because that's really, really small force, small torque. So we're not building that. But we are going to use some of the design features that are in mechanical clocks. And we need to drive the torque higher. So there's going to be some changes here. And the big change is we're not looking for an 8-day runtime. We're probably looking at 12 to 24-hour runtime. And that's it for now. I'm pretty excited about where things are headed. I'm trying to keep things economic when it comes to the budget, right? I don't want to have to reinvent the wheel. It's kind of funny. Kind of am reinventing the wheel here. We're going to be taking some existing technology that's been around a long time, okay, and applying some new thoughts and thinking outside the box to try to accomplish a goal. And the end here is, or I should say currently, I don't know if this is even doable. But like I said earlier in the video, that's the fun, is exploring and find out whether or not this is possible. I have some ideas on already approximately how much wattage would be generated. We're talking pretty low wattage. It might be like 60 watt hours. somewhere in that area. That's not very much, but I'll talk about why that's not as important as it seems. And we'll talk about how that can be multiplied potentially. All right, that's it for now. Hope you enjoyed the video. We'll talk to you all real soon again next time.